Okay, so last time we talked about regular expressions. We said they're equivalent to finite automata. For every regular expression, you convert it to finite automata using these composition rules, base cases, and the composite operations, union, concatenation, and Kleene closure. Basically, we gave an example where you convert a regular expression into a finite automata. Then we minimize the finite automata by looking for equivalent states. Once we do that, we got smaller and smaller equivalent finite automata recognizing the same language. Finally, here we end up with a pretty small one. In general, you could do this with a pretty straightforward algorithm, n log n, where's the case, n is the number of states. Minimizing pushdown automata or Turing machines is undecidable. We'll talk more about that later. And basically, any finite automata can also be recognized or denoted in terms of the language it recognizes, denoted by a regular expression. That conversion is a little more involved. We talk about regular finite automata that has a generalized expression on each one of the arcs. Rather than a single character transition, you can transition on regular expressions more generally. You start with a regular finite automata and then you convert it into a generalized one, and you get rid of triangles by composing and merging states and arcs. And eventually, once you do this enough, you have a single start state, a single finite final state, and the regular expression denoting the language recognized by the finite automata ends up on that single arc, and that's how you can generally convert a finite automata to a regular expression. So that gives us two equivalences in terms of characterizations. Every regular expression has a finite automata that accepts a language denoted by it, and every finite automata has a regular expression that represents the language accepted by that finite automata. So it's a two-way street, and therefore regular expressions and finite automata both characterize the exact same class of languages, namely regular languages. So we also went over some regular languages and finite automata decidability problems. Whether a language of a machine is empty, we do that using graph reachability pretty straightforwardly. See there's a path from the start state to a final state that reaches it. And then a language is infinite if and only if there's some cycle from which you can reach a final state, and from a start state you got to be able to reach that cycle, and that cycle better be not epsilon cycle. And then the language is infinite, and it's also pretty straightforward to determine whether the language of two given finite automata, the languages are the same or not. Basically, you take the pairwise set differences in the languages, construct finite automata for them, and see if both pairwise differences are empty. So if and only if the two languages are the same, and for emptiness we use substitute from the first. So lots of expressions, machines. There's properties of them that we can determine algorithmically pretty straightforwardly. Right now we're not talking about efficiency even, just what's doable and what's not doable. Because for Turing machines, all these questions are not decidable. In fact, for pushdown automata, maybe most of these kind of questions are not decidable. Okay, so that kind of summarizes regular expressions, finite automata, at least the basic properties. We also talked about closure properties. And now we're ready to talk about context-free languages. Any questions so far? So this is in a few minutes the summary of the last couple of lectures. So context-free languages, basically we'll start with context-free grammars. Grammar is a set of production rules and a way of transforming sentential forms into new forms, given those rules in a way to produce strings. So a finite set of variables is the basis of the grammar. We call them V1 through Vk. Set of terminals, which are separate from the variables. Variables can be substituted with other things. Terminals stay. They're like, well, terminal symbols. They are the end result of a series of variable transformations. Then a finite set of productions, we'll see an example of this in a minute, a start symbol and a bunch of production rules. So this kind of mimics the way a finite automata works, or any automata works. There's some states, those are your variables. The productions are basically the transition rules, equivalent. Start symbol is like the start state of the machine, and so on. And so you apply basically transitions or productions in the case of grammars to partial forms, and you get new forms. So if you have a variable vi, you can apply the rule vi goes to some string of variables and terminals, and the vi gets substituted by whatever that is, this delta, the change in what the variable vi is going to be replaced by. And it's replaced regardless of context. So whether it's in the context of some alpha and beta or not, doesn't matter. This vi gets substituted blindly by this delta according to this transition rule, regardless of context. That's why it's called context-free. Because it doesn't have to be context-free. It could have been context-sensitive, and based on the alpha and the beta, it could have been different rules based on what the alpha and the beta are, dependent on the context, and then it'll be context-sensitive. But that's a whole new, more complex set of production rules, and those kind of grammars, context-sensitive grammars, can produce languages that context-free grammars cannot produce. They give you more. They can recognize and produce more elaborate languages, more complicated languages. So here's some examples. Consider these three production rules: S goes to SA, S goes to SB, or S goes to epsilon. What kind of a language can this grammar produce? Well, first we denote it a little bit more succinctly like this with bars. So if S goes to several different things, we can denote it like that a little bit more shortly or succinctly on the same line. So a derivation in a grammar is a bunch of production rules repeated and applied over and over again until you get only terminals and no more variables. So for example, you can go S goes to SA applying the first rule, or you can go, then the S goes to another A applying the first rule again. In this case, the S goes to epsilon, and so the A is left by itself. And that's it. That's a string derived in this grammar, produced by this grammar. You can go S goes to SA, applying the first rule, then apply the second rule, S goes to SB, and then S goes to SA again, and so you have ABA after the S, and so on. And finally, the last S goes to epsilon, and you get the string AABA. Right. So how would you characterize all the strings derived in this grammar?
A or B star.
A or B star. It's any string whatsoever. How many can see that? Okay. Any questions so far about what a grammar is, how a grammar works, the language it yields or produces or induces? Is simply the set of all strings that are possible to derive within that grammar, starting with the start symbol. In what order do you choose the rules? Arbitrary. You get to choose. Non-deterministically, you pick a rule up and you apply it. You can apply any other rule instead. And the grammar produces a language that's the result of any possible production whatsoever by application of the rules in any possible order you'd like, all of them. Okay. So those are strings in the language here that you end up with only terminals and no variables. Those are the final strings that you produce. So a string is generated in the grammar if some derivation yields that string with some series of substitution rules applied, or production rules. And the language is what I just said, generated by a context-free grammar is a set of all possible strings that are derivable in this manner inside the grammar starting from the start symbol. So, for example, here, this previous example, the language is AB star, sigma star. It just so happens for this particular example. And language is context-free if there exists a context-free grammar that generates it. Now that's not a vacuous definition, because some languages do not have a context-free grammar to generate. An example will be 0 to the n, 1 to the n, 2 to the n. That's not a context-free language. There's no grammar, no context-free grammar in the universe that possibly generates that. We'll prove things like that soon enough. Similarly, WWR is a context-free language, a string followed by its palindrome, by its reversal, which together give you a palindrome. The set of all such palindromic strings is a context-free language, but the strings of the form WW is not a context-free language. No grammar can generate that, no context-free grammar. Okay, so therefore sigma star, through this grammar proof, is a context-free language because it's a context-free grammar it generates. Okay. So here we're talking about the palindromes. So these words are all palindromes. Step on no pet's interesting. It reads backwards the same as forwards. Try it. So how would you design a grammar that generates such strings? Not too hard. basically you generate both ends around the middle, make sure that both ends are the same. So S goes to ASA, or conversely, alternatively, to BSB, or to A or to B or to epsilon. These are the final terminating rules. So you apply the first rule, go ASA, and then S goes to BSB right here in green. It's color-coded for your convenience. And then finally, that S goes to epsilon and ends up with nothing. And you have ABBA, which is a palindrome. And you can prove that not only this language will generate palindromes, it will generate all palindromes, not just some of them. Okay, so it satisfies this definition. A string that reads backwards is forwards, and it'll produce even length palindromes or odd length palindromes, both. Right? Any questions about this grammar, what it does, how it works, and why it makes the palindromes taken all together a context-free language? Pretty straightforward. Okay. So, how would you represent, say, the set of strings that denote all well-balanced parentheses, where the parentheses are well-balanced? So again, you generate, you create rules for generating nesting and juxtaposition of parentheses like this. SS, that's kind of a juxtaposition. Parentheses, S parentheses is a nesting rule for parentheses, and of course you gotta terminate somewhere with the epsilon. So this simple grammar here, short though it is, generates all well-formed parentheses. So here it generates parentheses, 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 parentheses. Open, close, open, close. Here it's open, open, close, close. But what it will not generate is close, open, open, for example. That's not well balanced. Not only the lefts have to match the rights in number, but they have to match them in context. So you can't just say close, close, open, open. That's not balanced either, even though there's two of each. I mean, get this. Okay, and this grammar will do the job. So it generates only well-formed parentheses, and all possible strings corresponding to well-formed parentheses will be generated from this simple, relatively short grammar. Now, just so happens that this grammar is also a bit ambiguous. We'll get to that in a second. But here's an alternate grammar, parentheses, S parentheses, another S, or epsilon. This grammar, too, will generate all well-formed parentheses. But it's shorter in terms of production rules, right? This has 3 production rules here in this first grammar, G1, but grammar G2 here has only 2 production rules, this one and this one. If you want to count characters, this is 1, 2, 3, 4, 5, 6 characters altogether, maybe 7, 8 if you count these 2. Here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a longer grammar, more characters to represent it. So sometimes you can minimize a grammar, but generally minimizing a grammar is not decided. It's really hard to do. In fact, impossible to do algorithmically. All right, so design a grammar generates all valid regular expressions. Now remember, a regular expression is a string with parentheses and pluses and stars and what have you. But how would you generate regular expressions and all valid regular expressions? Well, you'll have S goes into xi for each symbol x of I, for all symbols in the alphabet sigma. And then you'll have a generation rule in the grammar of the form parentheses S parentheses, juxtaposition of S's right here. That's the concatenation in regular expressions. Right here's a clean closure with S and a star, and here's the union operator plus between 2 regular expressions, S on either side of the plus. So, for example, in the alphabet AB, here's some derivations, right? S can go to S star, this inner S, this S can go to parentheses, S parentheses, applying the first rule here. And then this S here can go to S plus S, applying the 4th rule there, and so on. And finally, the first S goes to an A, and the second S here goes to a B, and that is the application of this first rule and the first production. And similarly, a different production could be S going to SS, and then 4 S's, and then one of them will go to an A, one of them will go to a B, right? The third will go to an S star, the 4th will go to a B, and finally this S will go to epsilon, or to A rather, and end of story. So the set of regular expressions is a context-free language. Now remember, what regular expressions represent, not what they are, but what they represent are the regular languages. So that's not to say that the regular languages together are context-free language. It will be a type error to say the regular languages are context-free language. They're not. The regular language, each one is a language. Now, it just so happens that the regular language is also a context-free language, separately from this. But this context-free grammar generates syntactically all valid regular expressions over some alphabet sigma, and that makes the regular expressions a context-free language in and of itself. Any questions about any of this? How many understand this perfectly? Okay, any questions? How many have seen this before, all of this before? I'm just curious. Okay, half of you, all right. That's why we're here, so we're covering this relatively quickly. Okay? Ambiguity. So ambiguity is not a great thing to have. Some sentences are ambiguous, some symbols are ambiguous. This is turning upside down and it reads the same, if you look carefully. It's the word ambiguity written upside down and right side up, amazingly identically. And there's lots and lots of examples of ambiguity. You say, I like dominating people. That's an ambiguous statement. You don't know if the word dominating is a verb or an adjective, right? In arithmetic, you say A minus B plus C, unless you had order of operations kind of rules, that's an ambiguous statement. You don't know if it means this or if it means this, which operation is done for. And they have two different meanings, mathematically, arithmetically, numerically, if you do the order one way or the other, right? In a programming environment, it's like if P then, if Q then S, else T. But you don't know if it's grouped this way or this way, right, in a programming language, unless you have some contexts that disambiguate it, using parentheses or braces or whatever. So ambiguity in general should be avoided because it obfuscates the meaning of what you intend to say, right? If you say, I like annoying people, that's an ambiguous sentence. How many see that? You don't know if you mean annoying is a verb, like I like to annoy people, or I like people who are annoying. That's less likely, but you don't know from the context which one you mean unless you further explain it or identify and the ambiguity and eliminate the ambiguity, which is what we like to do. So even in language, there's all sorts of funny ambiguous posters, right? I love ambiguity more than most people, right? Eat here and get gas, right? That's an ambiguous statement. No parking violators will be towed, right? Call me a cab, okay, you're a cab. An ambiguous assertion, right?
Singing in the rain.
Which one?
The line, call me a cab, okay, you're a cab. This line in the movie Singing in the Rain.
Oh, Singing in the Rain, okay. Yeah, so she remembers it from the movie. So it makes good humor, actually. It's funny. But nevertheless, the intention is kind of ambiguous, right? Famous song, Lola by the Kinks. One of the last lines is, I'm glad I'm a man and so is Lola. It's not clear if Lola is a man or Lola is also glad that he's a man. Probably both, if you know the song. And there's ambiguity in art, which makes kind of really interesting aesthetics. These are ambiguous art. So each one of these can be viewed as figure and ground in several different ways. This looks like a skull, but if you look carefully, it's two women here, right? This looks like a skull again, but it's two people riding a sleigh. Right? Here, you don't know if the animal is looking this way or that way. How many can see those ambiguities? Sometimes it's hard to tell visually what's going on unless you kind of focus and squint your eyes and see what's going on. Right? There's some ambiguity there. Right? Here, you might see a dog. How many can see the dog here? Okay. It's not easy to disambiguate these images, right? Feels like Don Quixote, right? A windmill, but also his face. Right? This could look like a young lady looking away or an old lady looking forward. So some of these are famous, actually. It's like psychology tests. Sometimes they give you these images, and based on what you see, and then they make certain pronouncements about your personality. Escher used to have a lot of ambiguous figure and ground kind of plays. Here's good and evil written together on top of each other, figure and ground, based on which you focus on is the one that comes to mind. Again, some faces represented as skulls or nature scenes. This one says optical illusion, playing on figure and ground. So it's kind of a cool one right there. Here you can't see if the guy is looking forward or sideways. Either one makes sense depending on what you want to focus on. So ambiguity is, can make interesting humor, interesting art, but in terms of grammars and languages, in programming and math, you don't want ambiguity because it degrades preciseness and degrades intention and sidelines, deliberateness and precision. So a grammar is ambiguous if some string in it has two different derivations inside the grammar, right? So some context-free grammars are ambiguous. So for example, take this grammar here. We've seen this grammar, actually, so this is a pretty straightforward, trivial grammar. S goes to SS or epsilon. What's the language of this grammar? All you can get is the empty string out of it, no matter how much parsing you do and generation, application of rules of generation of strings you do. But epsilon has many, many derivations here. Here's one derivation, goes straight to epsilon from S, or go to SS and then SSS, and even that has multiple derivations, and then each one goes to an epsilon. So it's a highly ambiguous grammar. And some grammars are not even that trivial, and they're still ambiguous, right? So here's a non-ambiguous grammar for this language represented by this grammar, or generated by this grammar. Just have a single rule going S goes to epsilon, and then you're good. There's no ambiguity, right? But that was in a happy case when we identified the ambiguity and got rid of it deliberately. And sometimes the grammar that is not ambiguous will be even longer and more complicated than the ambiguous one, not necessarily simpler. Sometimes there's a cost to removing the ambiguity. So for example, if I want to present the language A star as a grammar, the context-free grammar, here is one possible grammar, SS and A or epsilon with respect to what S can go to. So S can go to SS, each one goes to an A, that's one derivation. Here's another derivation of the AA using another rule with the epsilon in it. So it's ambiguous, and you can write the grammar in an unambiguous way, for example, this way. This grammar too generates A star, but it's a non-ambiguous grammar, so it's preferred. Okay? Well-balanced parentheses. So the grammar we've seen before, this grammar here, is ambiguous. How many can see it's ambiguous? Yeah. Many ways to derive certain strings in here. Like for example, to derive this string, you can do it this way, or you can do it some other way like this. You can do the same string, parentheses, parentheses, open, close, parentheses, but multiple distinct derivations, different derivation trees. And so it's an ambiguous. Here's a non-ambiguous grammar for the same language. We've seen this before a couple of slides ago. It's not necessarily trivial even to prove that this grammar is the same as that grammar. It'll generate all well-balanced parentheses. Something you need to prove, that every well-balanced parenthesis has a derivation in this grammar. And this grammar will derive nothing but well-balanced parentheses. So it's equivalent to the first. But at least this one's not ambiguous. There's only a unique way to derive any set of well-balanced parentheses in this grammar G6 here. Well, G5 gives you the same language, but it's ambiguous. It has ambiguity. So for context-free grammars, some of them are ambiguous, and for some of them, the ambiguity can be removed by deploying a non-ambiguous grammar instead, like we just did in these examples. The ambiguity can be removed. But here's the bad news, that some context-free languages are inherently ambiguous. In other words, any context-free grammar that generates that language, and there's plenty, there's always plenty of different grammars that generates any particular language. You can always pad it out with epsilon rules and all kinds and many other complicated rules that will do nothing more to add strings to the language. But there are some languages generated by context-free grammar, but any context-free grammar that generates them is inherently ambiguous, and there are no non-ambiguous grammars. None exist. And so the problem of ambiguity is not just in the grammar, it's in the language itself. And that's a worse kind of ambiguity. In the first case, it's the grammar's fault that it's ambiguous. In the second case, the grammar is not at fault, because there are no non-ambiguous grammars that generate the same language. And the fault is in the language, it's inherently ambiguous. And that's worse. And some context-free languages are inherently ambiguous. That's another thing. This is not easy to prove, actually. So for example, let me give you an example of this. So the language A to the N, B to the N, C to the M, D to the M union with all A, B, C, and D's nested instead of this way, N, N, M, M, they're nested this way. M, N, N, M again, if you take the union of all such strings, that's an ambiguous, inherently ambiguous language. There are no non-ambiguous grammars for it. And here's another inherently ambiguous language right here. A to the n, b to the m, c to the k, where either the first two are equal or the last two exponents are equal. Turns out that's also inherently ambiguous. Now these are not easy to prove, but for extra credit, if you feel ambitious, maybe try to prove that they're inherently ambiguous, these two. Or maybe look it up even and see if you can understand the proof that you can find. It's not particularly interesting. But it turns out that detecting whether a grammar is ambiguous or not, it turns out to be undecidable. Again, for extra credit, try to prove it, or maybe look it up and see if you even can understand the proof that you find online somewhere that ambiguity, to detect ambiguity in a grammar, even a grammar, the question is whether it's ambiguous. Is there a string that can be derived two different ways inside the grammar? Undecidable. There's no algorithm in the universe to determine that. So in some sense, we were very lucky to detect the ambiguity in his previous grammars that we've seen as examples, simply because they were small and trivial and not a whole lot going on. Just like the halting problem, you can solve it for very specific cases, like programs without loops, or things that obviously halt or obviously have infinite loops. Very special cases, same for ambiguity in grammars. So I'm just bringing it to your attention that that's what's going on. Now, why is all this important even about ambiguity? Grammars are used all over the place, right? Grammars are used inside compilers to parse code. How many know that? Right? So it's important that there's no ambiguity in these grammars, otherwise your code will be parsed two different ways with two different semantics, two different meanings. Like arithmetic expressions become ambiguous, or if then else they become ambiguous, and then you have trouble trying to code things. So the syntax of a language itself should be represented by an unambiguous grammar. Right? And the language itself, first of all, should not be inherently ambiguous. That's a given, right? Like English is inherently ambiguous. If you say, I like annoying people, well, that's an example of ambiguity, or many, many others. A programming language, not so much. It better be not ambiguous. The language that constructs, that represents all valid programs should definitely not have ambiguities in it. And moreover, the grammar that the language is specified under, like the grammar that specifies all valid, syntactically correct C or C++ or Java or Python programs, better be not ambiguous in grammar. Otherwise, the compiler will have trouble parsing code unambiguously. There's many other contexts where grammars arise and ambiguity is not a good thing and should be eliminated. But again, generally it's hard to do. Some famous programming languages, were thought to be unambiguous until somebody found an example where they were ambiguous, and that created a lot of issues for compilers and for implementers, and created bugs in code. Any questions about any of this? So now we start talking about pushdown automata. So pushdown automata essentially are finite automata with a stack. Right? So everything we said about finite automata holds here, but they have an additional component that's a stack that you can push things onto and pop things from. And in the book, in terms of pages, we're page 109, 110, 111. So please read the book along with the classroom discussions, and as you work the homeworks, also refer to the book as well. So formally, a pushdown automata is like a finite automata with a stack, and you have all the components of a finite automata. So you have a set of states, you have an initial state, you have final states, you have an input alphabet, and the stack alphabet could be different than the input alphabet. It's an option that you have. It could be the same alphabet, but it could be different. That's an option. The transition function is a little more involved in a finite automata because it also includes the stack optionally as a way to change states, and the way you change states now depends on what's on the top of the stack as well as what's in the input and which state you're in at that moment. So the type of the transition function takes you from a state and an input symbol in the input and a stack alphabet character, whatever's at the top of the stack, and it puts you in a new state, and you can replace the top of the stack by some other stack symbol or symbols. That's why you have the star, it can be multiple symbols. And this is 2 to that, which means it's a power set of the cross product here, which means it's any combination of state and stack alphabet strings non-deterministically, it can branch in several directions. So non-determinism is built right into the definition of the transition function. It's not something we do as an afterthought to see what would happen later, like we did with finite automata. Right? So non-determinism is essential here. It's built right into the definition. And why is it built right into the definition? Because it matters. Non-determinism is a superpower here. If you have a non-deterministic pushdown automata, that has more power than a deterministic one. Okay. So for example, the language 0 to the n, 1 to the n can be recognized with a pushdown automata deterministically, but other languages like WWR, palindromes, cannot be determined deterministically, cannot be recognized deterministically with a pushdown automata. Only a non-deterministic pushdown automata can recognize WWR, but it's still a context-free language with a context-free grammar that can induce it or generate it. So we need non-determinism built into the definition. With finite automata, non-determinism was an afterthought. We had deterministic finite automata defined first, and then we said, what if we allow non-determinism, and then we were able to eliminate non-determinism and create an equivalent deterministic finite automata. And what was the technique called? 2 words. Getting rid of the non-determinism in the finite automata, making it deterministic. How many of you remember that? Really? Only 3 of you? Wow. Let me not be presumptuous. What is non-determinism?
Allowing epsilon transitions and
multiple next states, right? And if you allow non-determinism in finite automata, it seems like it can do more, but it turns out it can't. You can always take a finite automata that's not deterministic, beat on it, and convert it into an equivalent finite automata that's completely deterministic, that will accept the exact same language. What technique was used there? Do you remember? Close. Power set construction, which is a generalization of cross product, because you can have superstates on many states, not just 2. A cross product was like to find the intersection, but the power set is to track all non-deterministic branchings all the way out. So why can't you do power set construction here to get rid of the non-determinism? We'll talk about that in a minute. All right, but you also have an initial state. Of course, you got to start somewhere. I'm using color codes here to denote things, so same as the color codes in the finite automata. Initial state is always purple. It's a little arrow going into it. Transitions are always blue. Blue is a nice color. We use that to denote transitions. Right? And final states, we use red and double circled ovals to denote final states. Of course, the final states are some subset of all the states. The initial state is a single state, an element of Q. F is a subset of Q. And the pushdown automata is simply those set of 6, it's a 6 tuple, an ordered 6 tuple, right? The set of states, the input alphabet, the stack alphabet, the transition function, the initial state, and all final states. Together, they completely specify the pushdown automata. And of course, we already mentioned non-determinism is inherent in the definition. Any questions about any of this? So it's like a finite automata with an extra feature of a stack. We'll see examples of that in a minute. Yeah.
Is the deterministic pushdown automata, the language is generated by that? Is there a difference between those and the?
Yeah, it's a subset of the general languages generated by non-determinism.
Is there a name for it, or is it just?
It's called deterministic context-free languages, as opposed to context-free languages in general, which may include non-deterministic ones. So for example, 0 to the n, 1 to the n is a deterministic context-free language. It's context-free, and there's a deterministic PDA that accepts it. There's also non-deterministic ones that accept it, but in particular, there's a deterministic one that accepts it and makes it deterministic context-free. So the deterministic context-free is a small subset of the context-free. They're both infinite. But if you open it up to non-determinism, there's a whole lot more you can do. Like I already mentioned, palindromes, for example. You can't recognize palindromes deterministically. And we'll talk about examples of that in a minute. So a pushdown automata can use its stack as a storage mechanism, but it's a very restricted storage mechanism. It's a LIFO, right? Last in, first out, because it's a stack, right? So because it's a stack, it's basically using pushes and pops. So you can push to the top and pop from the top, but you cannot go all the way to the middle, and certainly not to the beginning, without popping everything first. So it's a lot like, you know, trays in the cafeteria or plates in the cafeteria. You can only access the top tray or the top plate, and only it's like spring-loaded, a big stack of trays. How many have seen that in cafeterias? If you try to get to the middle and pull a plate out in the middle, something terrible might happen. You know, the whole stack might fall over, there'll be an upset or two. So it's a very restricted kind of way of accessing things. And the read-headed input goes one way and one way only. It goes left to right, same as a finite automata. It can't go backwards, like a Turing machine can. And when you're in a final state, you can accept, and then if you'd like, flush the input and flush the stack if you want to do that. So a PDA, pushdown automata, PDA, can be made deterministic, but if you restrict the transition function to only unique next moves. But now it has less recognition power. There are languages now that those kind of pushdown automata that are bounded to be deterministic can only be recognized if you disable the non-determinism option. Okay. So it turns out that you can prove that if a language is accepted by some context-free grammar, there's also a PDA that accepts it. Conversely, if a language is accepted by some PDA, there must be a context-free grammar that generates that language too. So these are the two characterization theorems that parallel the two characterization theorems from finite automata and regular languages and regular expressions. So in regular expressions, we said regular expressions denote the exact same language set of languages that are accepted by finite automata and vice versa. And all the languages accepted by finite automata are exactly the regular languages, those are denoted by regular expressions. Here you have a pair of characterizations, and it's an if and only if again. Here's a little bit more involved to prove, but I'm going to leave it to you as an exercise to go deeper into the proof if you'd like. You know, you can prove each one separately. But they kind of parallel the kind of proofs and logics and inferences that we made about the characterization of regular languages as regular expressions on one hand and finite automata on the other hand. So language is context-free if it's only acceptable by pushdown automata as an if and only if. Right? So it's a complete characterization. So context-free grammars and PDAs have equivalent sort of expressiveness or computation power or recognition power of languages. Again, mimicking the finite automata and regular expressions case. Okay, so that's so please know that. You know, it's we'll use that, you know, many times in what's coming next. All right. So let's talk about closure properties of context-free grammars and context-free languages. Same as we talked about closure properties of finite automata. Remember, we talked about finite automata, regular languages, regular expressions. We said the regular languages are closed under union and under intersection. How did we prove the regular languages are closed under, say, intersection?
Cross product.
Cross product. Under union, how did we prove that?
We can either use cross product construction.
Either cross product?
Or
Someone want to give me a hint?
that property.
A property, what property? Some identity, which identity? The Morgan's law, yeah. That's what you meant, the Morgan's law. So we're going to have similar kind of proofs here. So let's see how these proofs work. So the context-free languages are closed under union. How would you prove that? How many understand the question? I don't know the presumptions. Okay, so we have two context-free languages. They're union, they're sets of strings, and the union is also context-free.
Can the union be considered as an OR operator, and therefore it's accepted by either that or this? You can non-deterministically split your way through and your answer.
Yeah, you can do that. So he's basically having a PDA-based proof, pushdown automata-based proof. He's saying, take the two pushdown automata that recognize both languages that we're talking about. These intersection is going to be also context-free. So each language is context-free, so it has its own PDA that recognizes it. Have a super PDA that non-deterministically either applies that one or that one to the input. And together, that super PDA that chooses that one or that one, arbitrarily, non-deterministically, to the input, accepts the union of both languages and it's a big super PDA, which is just a PDA, push on automata, and it uses non-determinism, which is okay. PDAs can use non-determinism, and so that proves that the union is context-free as well. How many understand that? You can do that. Somebody give me a different proof altogether. You got a question? Yeah.
No, yeah, I was thinking maybe we can create a new context-free grammar.
Yeah.
So we will have a new start symbol and give this symbol 2 rows.
Yeah.
From this new start symbol to generate either to the start symbol of the first language or to the start symbol of the second one.
Yeah, absolutely. So if you have, in grammar 1, you have some start symbol S1 that does something. In grammar 2, you have some new start symbol S2 that a bunch of other rules following that. Right? So together, you can have some new super grammar that goes to either S1 or S2. Together with all these rules, this is a new grammar, G prime, and this new grammar, it goes to either this grammar or that grammar. Together will generate, everything is generatable by either grammar. How many get that? Which kind of parallels the proof with the PDA, except now it's a grammar-based proof, which is a different proof, but it's the same strategy. It's kind of parallelize, go both ways at the same time. One little caveat or warning here. What do you think can glitch if you do this blindly? Just add this super rule and keep these 2 grammars around.
Second grammar might not.
What about the second grammar?
The second grammar might not ever be part of the rule. So like it could be an S1 like all the time, and S2 might never be reached.
So this grammar and that grammar can have some of the same variables in them. This can have a variable Q and T and G, and so does this. And now the 2 grammars begin to clash and mix up in ways that you didn't intend. How many get that? Just like in a programming language. If you write a program and you write a program, and I want to use both of your programs and just put them together in one giant pool of code and just arbitrarily call your program as subroutines, it seems okay until you realize that you could have used some global variables that he used too with the same names, and now when you set them and he uses them and sets them, and it begins to clash across this boundary, and that's no good. How many understand this is bad? But it's easy to avoid. How will we avoid it in the programming context? Change the names of all the variables. Call them X, whatever his names, and Y, whatever his names are. Now you're guaranteed unique names. You don't have to worry about clashes anymore in global variables. Same thing here. You can rename all these variables in this grammar to be different than all these variables in this grammar, and renamings don't matter. It's the variable names in the program. It's pointers to locations. There's nothing special about names. Right? You can call the names A, B, and C, or alpha, beta, and gamma, or meeny, miny, and mo. It doesn't matter. Okay, so you can derive a grammar for the union, or you can do it machine-based PDA. Any questions about these 2 different proofs that we just went through? And so you see the hang of it. The context-free grammars are closed under Kleene closure. How would you prove that?
It's just unions, a set of union operations. So.
Yeah, but it's an infinite set of unions,
yeah.
right? So you have to be a little careful. So what kind of a proof technique is it? Is what is based on what? So first of all, give me a grammar-based proof. That if a language is context-free, the Kleene closure of that language is also context-free, necessarily. Was this first theorem true for regular languages? Was regularity preserved under the union? How many say yes? Yeah. Is the second theorem true for regular languages? Is regularity closed under Kleene closure? How many say regularity was closed under Kleene closure? Really? Only 2 of you can say that? Then let's not even talk about this. Let's talk about the other one, about regular language. So why are regular languages closed under Kleene closure? Give me 2 different reasons, 2 different proofs.
You have a DFA associated.
Okay, so if you have a DFA associated with it, why is the Kleene closure also a regular language? Kleene closure of a regular language is regular.
Transitions from the final state to the initial.
Yeah, have transition from the final state to the initial state and cycle around. Okay, non-deterministically cycle around. Every time you reach a final state, you go back to the beginning and restart processing whatever the input is from that point on using the original. And if you do this non-deterministically in all possible ways, and of course from the initial state you got to escape to an epsilon transition to a really final state and then do nothing more. That gives you the epsilon base case in the Kleene closure. How many get this? We've done this proof, right? It's only been a week, right? We've done all. All right. Could you pull a trick here with PDAs?
Yes.
How many say yes? How many say yes? That's better. Any issues with that? What would that entail? Well, start processing the string, execute the PDA. When the PDA reaches a final state, even if it didn't reach the end of the string, what are you going to do? Go back to the beginning, but empty the stack first so it doesn't mess you up. You're resetting the PDA to its initial state, and then you continue the input from there. And every time you reach another final state, do the same. Empty the stack, flush the stack, don't even look at it, just flush it, empty it, go back to the beginning, start processing again and again and again. And either you reach the end of the input, and you better be in accepting state again, or before you even do any of that, you can just accept it, that's it. Because the Kleene closure will always have the empty string in it, even if the language doesn't. So same trick as for finite automata, except now you're doing it with a PDA. How many get this? Any questions about this?
Oh, we can write a grammar which is actually easier.
Yes, now let's do the grammar. So now this is the second proof, completely different than the first. How would you do it with a grammar?
We have a super start state which goes.
Yeah, so let's say you have a grammar that takes S into some blah, blah, blah. So now you have a super grammar, G prime.
Which goes to either S or epsilon.
So S prime
goes to an SS
go to an SS
or epsilon.
or epsilon. So here with a super grammar, you're going to multiple copies of the initial symbol, the initial variable of this old grammar, as many as you want, and finally epsilon. And each one of them gives rise to a whole string inside this original grammar. How many understand this proof? So this basically cycles the grammar an arbitrary number of times over and over, any number of times. Not just 2 times or 5 times or a rule time, but any number whatsoever. Not an infinite. Infinite is not a number. Okay, so we gave 2 different proofs why this is true, why the context-free languages are closed under Kleene closure. Okay. We gave a machine-based proof, a PDA, and of course we gave a grammar-based proof separately. It's good to prove things multiple different ways to make sure it all jives together, it all makes sense, it's all consistent. Sometimes you will try to prove it 2 different ways. You may observe that one way proves it and the other way may disprove it. And then what are you going to do? What does that mean? If you try to prove something 2 different ways and one way proves it, the other way disproves it, what just happened? What are you going to do next? What does that mean?
Undecidable.
It's undecidable? Is that what it means? No, that's not what it means. Sorry.
The axioms are inconsistent.
Well, in a science fiction kind of scenario, yeah, you may be the lucky mathematician who proved that the axioms are inconsistent and, you know, win a Turing Award, a Fields Medal, and the Millennium Prize all at the same time. But, you know, in a more likely scenario, what would be?
You made an error.
You made an error. So either one proof is wrong, or the other proof is wrong, or both proofs are wrong. So you got to go back. So that's one of the advantages of trying to prove things different ways, to make sure consistently you get the same results and everything matches and meshes with what you already know to be true from the other direction and so on. It's confirmation. Right? If you want to program a piece of code that's very, very important, like the piece of code that controls your heart pacer, the piece of code that runs in your chest, 50,000 lines of code that determine your heartbeat in the next second, in the next second after that. Or a piece of code that fires retro rockets where you re-enter the atmosphere from a space flight when you're going 25 times the speed of a bullet, but you weigh many tons of space. You know, that every millisecond counts, actually. Every microsecond counts. You're a few milliseconds late on the burn, and you end up in Africa instead of America because you're moving so fast. Or you might skip off the atmosphere altogether and end up on Mars. Not a good situation. But a piece of code is very, very critical. So what would you do to make sure you have very, very, very reliable code? Test. How do you test?
Simulate.
Simulate. But maybe the simulator is wrong. What would you do if your life, literally, if your life depended on a piece of code working correctly, no errors whatsoever? And you already know how code goes. How many ever written a piece of code that was correct the first time around? Like it's a substantial piece of code. I'm talking about hundreds of lines or more, not 3 lines or 5. Okay, it's very hard to do. Usually you have to compile it and run it again, compile it, you find errors, and even if you don't find errors, would you bet your life that there's no errors in there, even if you can't see them? No, I wouldn't. Neither should you, if you care about your health. Don't bet your life on these things. But some code our lives literally depend on. Space shots and even airplanes. You got an airplane, there's autopilot and there's all sorts of codes. The pilot doesn't do much flying, actually. It's the computers that do most of the flying. How many realize this? It's code that flies you through the air when you get on an airline plane. I don't know if it's comforting or reassuring. Often it's alarming because sometimes the computer crashes in midair. Hopefully the plane wouldn't crash too. So anyway, if a piece of code is very, very important, what would you do? You're an engineer, you're Boeing, you're a company, you're a government, you try to build really, really reliable piece of code. It's very, very critical.
So specification and verification.
Specification, verification, yeah. Maybe try to formally prove that the code is correct, but even then, what else could you do? Let's say the problem is very well defined. There's a certain input, there's kind of an output, and input-output behavior is very well specified, some function that you've got to implement. It's not something nebulous, it's no one way or the other, but it's got to be really, really, like you're implementing some mathematical function. And it's got to be 100% correct. Your life depends on it, literally. Any ideas? Yeah.
Use redundancy.
Redundancy. What kind of redundancy?
Like many different programs that are supposed to do the same thing.
Yeah. Take this task, this function you want to implement, give it to 5 different programming groups, or even 7. Each one will independently implement it without knowing that the other 6 exists, or the other 4 exists. 5 different implementations using 5 different languages, using 5 different compilers, on 5 different operating systems, on 5 different pieces of hardware, literally. None of them should talk to each other, or even know that the others exist. All 5 of them are on board your space shuttle. When it comes time to a critical decision, all 5 platforms with their 5 different operating systems, with their 5 pieces of software in 5 different languages, using 5 different compilers, implemented by 5 different groups, they all execute the same calculation, and then they see what all the other answers are. You get 5 different answers. If the answers are all the same, you're pretty sure that that's the answer. If 4 out of the 5 are the same and 1 is incorrect, what can you do? Or what can you conclude? Or you only have a few milliseconds to do something. You take a vote. You take a democratic vote over the outputs, and the majority wins, and you go with the majority, whether it's to fire the retro rocket or whatever it is to, whatever, this millisecond timing versus that millisecond timing. That's what you do. That's what people do, actually. Why is it important for all these groups to not just not collaborate, but not even meet or have lunches together?
There shouldn't be any bias.
Because if they start to talk and meet and exchange specifications and thoughts and ideas and talk, they'll probably share the same errors too. Because there'll be some groupthink and things will contaminate each other's thinking, so they should be completely independent. They should go strictly from respect, not even have lunch with each other, much less, collaborate and compare notes. Good question back here. Yeah.
What is the problem with simulating the code? For example, if you have unlimited time, you can simulate it like on every possible input.
Yeah, you can simulate the code, but the thing is, there's so many possible inputs that you can't simulate on all of them. So even something as simple as addition or multiplication, let's say multiplication or division, you can simulate a division circuit on every possible pair of numbers that you want to divide. But if you have 32 bits, it's 2 to the 32 possibilities for x and 2 to the 32 possibilities for y. So there's 2 to the 64 possibilities for x and y, and that's too large of a number to simulate. And you'll never know by exhaustive simulation that your division circuit is working properly. And if it's 64 bits, it's even more hopeless than that. So you cannot do exhaustive simulation even on something as simple as division. Never mind something more complicated function like cosines and tangents and square roots and or much bigger computations than that. Matrix inversion, just too many possibilities. In fact, Intel had a bad division hardware back in the 90s. How many heard of the FDIV Intel hardware bug? Oh, really? Nobody? It was one of the most famous hardware failures of all time. This was on the Pentium. How many heard of the Pentium chip? Okay. Back in the mid-90s, Intel realized, some guy who was doing a lot of heavy number crunching realized that the hardware Intel provided in their CPU doesn't implement division properly. In some cases, it made errors. Intel is a huge company, selling tens of billions of dollars worth of millions of microprocessors a year, tens of millions a year. And they made this mistake. It actually happened. It cost them billions of dollars to fix this. Because they had to recall and replace millions of CPUs that are already in the field. Very, very expensive, and also hurt their image and their PR and the advertising logo Intel Inside. How many heard the Intel Inside? That became a joke. People put that on the sides of toilets. Intel Inside, because you couldn't trust the hardware anymore. So yeah, simulation is good. Don't get me wrong. It's good to simulate and test. Very, very good. You can do it as much as you possibly can. But it doesn't catch all the errors. And it can't. There's just too many possibilities. And this actually happens in real life. In companies as large as Intel, and they should know better. They've been doing this for many decades.
Is there any way to just catch all the errors without simulation?
There's never a way to catch all possible errors. So testing could show you the presence of bugs. It can never show you the absence of bugs. You could bet your life that if you see a bug, it's there. That's pretty straightforward. But if you don't see bugs, it doesn't mean they're not there. You just haven't seen them yet. So it's not symmetric. Simulation can uncover bugs, but cannot prove that they're not there. It's like proving you're not a millionaire, right? You talked about it. Non-existence proof is very hard. And in testing, it's the same thing. And show you're a millionaire very easily. Show me the money. Show me the bugs. Showing no bugs, it's like trying to prove you're not a millionaire. Very hard to do. And when very, very important things depend on it, like nuclear launch codes and shutting down a nuclear power plant in case of emergency or whatever, you don't want bugs. And even if you don't see bugs, you can't be sure they're not there. And there's always special cases and exceptions that you haven't thought about, whether you realize it or not as a programmer. How many have seen that in their own codes? Special cases you haven't considered that come back and haunt you. You all have seen that, especially for complicated codes, not just 10 lines of code, but tons of lines of code. Also, some unsuspected things happen. Redundancy is very important. If Intel implemented two different multipliers inside or division circuits with two different groups using two different algorithmic techniques and two different hardware implementations, and both do the division, and if both disagree, they go to a third one or report some error or whatever, then it'll be a lot better. Of course, it'll be also more expensive and take more real estate on the chip and blah, blah, blah. There's a cost to that. Right? If you implement something 5 different times using 5 different teams and put them on a space shuttle, it'll be 5 times as expensive, roughly. But in terms of a space shuttle, it's already so many billions of dollars that, you know, preventing it from crashing or blowing up in midair, and that happened too a few times, is worth billions of dollars. But, you know, billions of dollars, the software is not the bottleneck in this billions of dollars. And certainly it's worth the effort. There was actually an interesting, you know, let me give you an example of an interesting case that programmers didn't think about, and it almost caused World War III. I'm not being dramatic. This actually happened. So at NORAD, the North Atlantic, you know, nuclear deterrent in the United States, has radar installations across Alaska that look over the pole. And they look in other directions too, because that's where the Soviet missiles would have come during the Cold War, 60s, 70s, and 80s. The missiles will go over the pole because that's the shortest distance from Russia to the United States, not across the equator. That's the long way. Anyway, so very powerful radars, programmed to detect swarms of ICBMs coming at you at the same time, and then triggering alarms. You have 20 minutes to take action. You know the rest. All of a sudden, there's a massive alarm going off, and the United States military scrambled bombers, B-52s with nuclear weapons, and put the missile silos on alert. They thought that the Soviets are attacking finally. And a few minutes later, we realized it was a false alarm. There was no swarm of missiles coming. Anybody can guess what it was or heard the story? And I'm not making this up. The moon rose over the horizon. The radars are so powerful they bounced the radars beam off the moon, and they thought the moon was the swarm of ICBMs coming. It has the same signature in radio waves, roughly the same size of a swarm of ICBMs, but same signature of return. The programmers never occurred to them to treat that as a special case. It just didn't occur. And if you think about it, if you were programming, you know, the radar installations and, you know, looking at, you know, would you think about the special case where the moon rises? Maybe you would, maybe you wouldn't. But you can see how they didn't. It's an interesting boundary, and it never came up in simulation. They never thought to simulate it either. But it happened. And there's probably other cases where, you know, similar things would trigger some alarm with possible catastrophic, you know, results. And nobody thought of this special case or this particular simulation of it. You can look this up. This, you know, we were about 10 minutes away from the next World War, from a full-out nuclear exchange, because of this software bug that nobody thought to test or simulate. And there's many other examples like that. I'm just giving you one dramatic one, but there's many other dramatic ones. Okay, so back to proofs. You know, that's and one more reason why you want to prove something 2 or 3 different ways, to make sure it all jives together, it all makes sense, they all reconfirm and test each other's hypothesis, and not just prove it one way and risk some error in the proof, and you never thought about this special case or this situation or this boundary condition or this exception or this hole in the definition, and you walk away in victory as if you won the lottery, but you're wrong. So always try to prove something 2 different ways, even 3 different ways, if you can. Okay, and that's what we're doing here. All right, the context-free languages are close on the direction with regular languages. How would you prove that? So you have a context-free language and you have a regular language, you intersect them together, the result is still context-free.
It's intersection, so it's definitely regular. Yeah. Is it? Or no?
Okay. Tell you what, answer it in 2 words. Why am I saying 2 words, by the way? That's a meta question.
Still a PDA still give a TFA without the stack. I mean, if I remove the stack.
Yeah, you can say a finite automata is a PDA without a stack, or a PDA that doesn't use its stack. That's equivalent. Right? How many understand that? That a finite automata is a PDA that doesn't use its stack. How many get that? Okay, good. Let me worry there for a second. So, if you have a context-free language, you intersect that with a regular language, the resulting intersection language is also context-free. 2 words prove it. And why am I saying 2 words, by the way? Hopefully you know me well enough by now to answer that question. Why am I not saying answer it in a full paragraph or 20 words or a tweet, 140 characters? Why 2 words? Really, all this time you heard me say 2-word proofs and you have no idea why? That's 2 words. And why Occam's razor? Because it forces you to focus on the most important words or concepts and trim away the fluff that doesn't matter much. It forces you to understand the crux of the matter, not all the fluff around it, thinking everything is on equal footing and just as important as everything else. No, it's not. Most of life is like that. A lot of fluff and a few very important things. And it's good to know which is which. So how would you describe a proof for this in 2 words? This theorem here.
Cross product?
Cross product. I buy that. How many buy cross product? All right, somebody else explain what he means. Now you can use a whole sentence if you'd like. Now we have the 2 words nailed down. By the way, if you need to use another pair of 2 words, a different pair of 2 words, what else would you say besides cross product? It's not the only pair of 2 words you can use. How many know what he means when he says cross product? Oh, just 4 of you. Okay. Well, I'm glad we're having this discussion then. You want to explain to them what you mean by cross product? I don't want to put you on the spot, but since you said it.
So you think of a regular, or like a DFA as a PDA that doesn't use a stack.
Mm-hmm.
You run them like in parallel, I guess.
Yeah, so what are you doing in parallel? Simulation in parallel, or parallel simulation, that's another 2 words that basically say it. So you simulate the PDA for the context-free language in parallel with the FA, the finite automata, for the regular language, in parallel. And technically it's a cross-product construction. How many get it now? And you accept. If either one accepts and the other rejects, you don't accept. If both reject, of course you reject too. But you only accept if and only if both accept. Both what? The finite automata on one hand and the PDA on the other hand, the pushdown automata. Now the finite automata doesn't need a stack. The PDA does, but you're the simulator. So you have your own stack as a simulator, and what do you do with your own stack to run the simulation? Whatever the PDA that uses a stack wants to do with the stack, that's what you do. You let it borrow your stack. And you're simulating both in a parallel simulation way in a cross-product construction. How many see this proof? It works. That was only half of you. Ask me some questions. Yeah.
But we are allowed only 1 stack.
You have only 1 stack, and
is that
the PDA will use that stack.
So that's the only reason why we're considering regular languages not.
Yes, we'll get in a second to the issue of intersecting 2 context-free languages. We're not talking about that yet, because that's more complicated. Some other issues there. But if you run a simulation of 2 things, one of which uses a stack and the other one doesn't use a stack, as a simulator, you just need 1 stack. How many get this? That's it. And if you use just 1 stack, you're a PDA too. If you're a PDA, you're context-free, and you're recognizing the intersection. So the intersection is context-free also. End of story. And that's a proof. Any questions about that? I didn't expect it to be that tricky for you. I mean, we'll repeat it as many times as we have to. I mean, that's what we're here for. But it's just like the 2 finite automata intersected their languages by doing a parallel simulation or cross-product construction, however you want to think about it. Questions about this? If you have questions, please stop. We'll go over as much as we have to, because things will only get deeper and more convoluted and harder. They won't get any easier as we go along.
Can we simulate the construction?
You can simulate.
Like the one we did for 2 DFAs with
Yes,
a
yes, it'll be
superset.
pairs of states.
Is it the similar construction?
They're very similar.
Okay.
That's why I said cross product. It's not so similar. It's the same construction, except you have a stack on the side
For one.
for one of them. Yeah. And if you're an accepting state in both, then you accept, and it's an if and only if, and together you've accepted the intersection, and you're a PDA too. You, the simulator, is a PDA.
How do you prove by simulation? Are you saying run cases? Because you can't prove something by exhaust all the cases.
Well, the simulation takes a string and runs both machines on the same string at the same time.
Yeah, but you only prove for one string. How do you know?
But you can do that for any string.
Arbitrary.
It's an arbitrary string. It's not a particular string like PDA. Take an arbitrary string W, run both in parallel on W. Whatever W is, the string W could be Shakespeare's Hamlet if you want, a very long string. Run both simultaneously together on the same string. They both change states. You keep track of the pair of states that both of them are in. One of them uses the stack, that's okay. That's why you got a stack and service the one that needs a stack. And together you simulate both simultaneously on the same string in parallel. Same as for two finite automata. Cross product construction. Question?
So as a result of like the side of it, the cross product of the language and then the language and the stack language?
It's the intersection of the two.
Okay.
The machines, you're crossing them together. By crossing, we mean the cross product of the state sets of the two machines respectively. But the language recognized by this cross machine is the intersection of the two languages respectively of the two machines. Same for a pair of finite automata bashed together. Here we're bashing together PDA and a finite automata as opposed to two finite automata. How many believe that, understand that, are okay with this? Okay, any more questions? If there are, let's ask.
One more.
Yep, sure.
So you're proving one specific regular language or PDA and FA, one pair of that, or it's a general?
It's general. For any PDA and any FA, you can do this. Which means for any context-free language and any regular language, this will work.
Okay, but we run
Let's harp on this point since you asked. So if we want to say that the integers are closed under addition, we're not saying that 5 plus 7 is an integer. It is an integer,
right.
But it's not just for 5 and 7. It'll work for 3, or for 20 and minus 13 too.
So the simulation is arbitrary string, arbitrary FA and PDA?
Yes.
Okay. How do you show that? I'm curious.
But we just did. You're simulating them in parallel. Right? Remember the cross product construction? Let's go back in time. This is fun. It's only a couple of lectures ago, but these are long lectures, so this will take a while. All right, so we're back to finite automata. Right? Remember this?
Yeah.
So this is completely general. The intersection of two regular languages is regular. Why? By parallel simulation, by cross product construction. Why? Because you can simulate one here, and together you're simulating both. This is not just for a particular string. It's for any string that you give. And it's not just for a particular one finite automata and a particular other finite automata. It's for any pair whatsoever. This is completely general. So do the same thing, except the first one is a finite automata and the second pushdown automata now.
Oh.
And it uses a stack, so there'll be a stack in here that it uses. But this is 90% of the proof is the same. Right? Is that how many understand that? This is how it works. Cross product construction. Yeah.
But so for the number of states of the cross product result, is the states of the pushdown automata not depend on stack as well, or does it?
It does. So when you make a transition, you have to refer to the stack before you make the transition in the PDA component. But in the FA finite automata component, you don't look at the stack because you don't need a stack because the FA doesn't have a stack. It doesn't know from a stack, so he doesn't need to look at a stack.
So is the number of supersets of?
So how many states are we talking about in this FA PDA combination cross product? It's a good question. How many? total number of states. How many states was it here?
N times n.
How many?
N times I. N times n.
It was the number of states of one times the number of states in the other, right there. Right? The new states of the construction is all the states of the first crossed with all the states of the second in all possible ways. So it's the product of the two state sets, sizes. In what we're doing now with the FA and the PDA, how many states are we talking about now? Same thing. It's the product of the two. How do you see that? Any questions about that? It's really very similar proof. Anything else for now? Yeah.
I have a question about
Yeah.
pushdown. So, precision of pushdown automata. The input is a tri-tuple state alphabet and the top of the stack, right?
The stack symbol, yeah.
So when we say the stack symbol, that means the top of the stack, not the whole stack, right?
That's right, just the top symbol of the stack.
Okay.
Yeah.
But the output is a cross product of states and the whole stack.
Not the whole stack. You replace the top of the stack by something of your choosing. Either another character, or either you push or you pop or you leave it alone. But that's the same as saying replace it by an extra pair of characters or a single character or no character. Replace it by epsilon is a push, is a pop. Replacing the top of the stack character with an epsilon is the same as popping it. Because epsilon is nothing and that character was something, right? Or you can put another character on top of this stack, and now you're pushing. Or you can leave the stack alone. Don't push or pop. That's also an option. But one character at a time. You push or you pop or you look at. You don't look at the rest of the stack. It's like trays in a cafeteria. You don't have access to the entire stack, just the top tray. You can take it or leave it, but just for the top tray. Or you put another tray on top of it, now you have one more tray on the stack. But you cannot take a tray out of the middle of the stack or push a tray into, put a tray into the middle of the stack. You won't physically even allow you to do that. The stack is usually in a cylinder, a metal cylinder or whatever. A stack of plates or stack of trays. So a stack is a restricted access mechanism. You can only touch the top. A queue is slightly different. You can touch both ends, but in a restricted way. In a queue, you can push on the top and pop from the bottom, or vice versa. You're not push and pop in the same place. Stack, you push and pop in the same place. You push, you pop at the same place. Queue, you push here and you pop there. Right? Both ends. So a queue is what kind of, so a stack is a last in, first out, LIFO. A queue is what? FIFO, first in, last out, or last in, first in, first out. Excuse me, yeah, first in, first out. So a line at your bank is what, LIFO or FIFO? Line in your supermarket. It better be FIFO, it's not going to be LIFO. So it's going to be a queue, not a stack. Otherwise, customers will be very upset. Think about it, If the last customer, in line got sort of first, everybody else is still waiting, they won't be happy. It happens, but not on a good day, and people don't like it. Okay, any other questions about this? Yeah.
Can we go through an example of the pushdown automata, because I don't seem to remember exactly how it works.
Okay, so pushdown automata. We have some examples on the slide. So let's go now. Fast forward in time, bring us up to present, and okay. So the close on the Kleene closure and close on the intersection with regular languages. Now, so let's talk about how they work, kind of as an aside. And I have some examples. Okay. So Let's say you try to recognize 0 to the n, 1 to the n. 0 to the n, 1 to the n. And you have a stack, and you have some PDA, it's a finite control, and this is on the input, 0 to the n, 1 to the n has a pointer to the input, and you can push and pop from the stack. How would you recognize 0 to the n, 1 to the n using a stack PDA? And by the way, a finite automata cannot recognize this. We will prove this separately by a pumping theorem argument. Let's leave it aside for now, but this is not a regular language, and a finite automata cannot recognize this, but a PDA can. How will a PDA recognize this language? Let's have other people participate. I don't want to call on people who get this one, but if the same 3 people keep impressing me, I keep wondering about the rest of you if you're following this. So let's have other people participate. Yeah.
First, when you see a 0, push it into stack and go.
All right. Whenever you see a 0, push the 0 to the stack.
And when you see 1, pop it.
When you see 1, start the popping process and pop the 1s against the 0s.
And when the stack is empty.
When the stack is empty and you run out of input at the same time, what do you do? Accept. All else, reject. So it's pretty straightforward, right?
But this PDA will accept 0, 1, 0, 1.
No. Because if it's 0, 1, 0, 1, it'll push the 0, pop it against the 1, and then all of a sudden you'll see something which is not a 1, but a 0, that's a rejection, automatic rejection. Or you'll see too many 1s and not enough 0s, that's a rejection too.
Why do you think that 0 will cause rejection?
Because we program it to cause rejection. So as long as you see 0s, you get to the stack. When you start seeing 1s, go to a separate state.
Okay, gotcha.
And start popping the 1s against the 0s on the stack, and never go back. And if you now see another 0 again, too bad, you reject immediately and stop. Flush the stack and stop. Or if you flush all the 1s and there's still 0s left on the stack, but you reach the end of the input and there's still 0s on the stack, reject again. So you only accept if they're an equal number and no other condition is true.
So we only need 2 states.
2 states will probably suffice for this. You may need to use a third. It depends how exactly what the transitions are. Yeah, but 2 or 3 states will do the job. End of story. It's pretty straightforward. In terms of lines of code, if you wanted to program this, again, a few lines of code, a loop with a few lines of code will do this. Instead of a stack, you'll have a counter. You'll count the 1s. You count the 0s. Increment the counter every time you see a 0. When you see 1s, decrement the counter. When you reach the end of the input, see if the counter is equal to 0. Right? And that's how a piece of code can recognize this too. How do you get that algorithm? It's pretty straightforward. Again, set the counter to 0. Count the 0s. Increment the counter every time you see a 0. When you finish the first one, start the decrementing process and keep decrementing every time you see a 1. If you reach the end of the input and the counter happens to be equal to 0, you accept. Any other condition, you reject. If the counter ever goes negative, you reject. If you see 0s after you're starting the decrement process, you reject again. How do you get this? It's pretty straightforward, right? Nothing too deep about that. But that's how PDAs work, using a stack. A stack is like a counter. But it cannot just count, it can also store characters in there, where a counter can just store a count. So a counter is a stack whose alphabet is what? The stack alphabet could be separate from the input alphabet, but the stack alphabet could be many characters.
Numbers.
A counter is equivalent to a stack with a certain property about its alphabet.
Numbers.
1 character only. How many get that? It's a tally. You know how people in prison sometimes, if they have a lot of time, you know how they count the days they're in prison? Like that?
Yeah.
Like, how many of you have seen that in movies? What kind of a count is that? What base are they counting in?
5. 1.
They're counting in unary, base 1. They're not counting in binary, they're certainly not counting in decimal. How many marks will it take to represent a jail sentence that's 10,000 days long?
10,000.
10,000 marks. That's the problem with unary counting. The representation is very large. If there were 10,000 days and they were counting in binary or in decimal, let's say they were counting in decimal, how many digits will it take to represent the number? 5. In binary, it would take how many digits in binary to represent 10,000? How many?
13.
About 14.
Log 2 of
10 digits in binary is 1,024. 8,000 is 13. You need the 14th digit to get to beyond 10,000. Anyway, a stack with a single character alphabet is like counting in unary, which is a counter. So if you can do this in a piece of code using one variable as a counter, you can do it using a stack too. How do you understand that? Now, not everything can be done with a single counter, even in code. Sometimes you need more variables or arrays or linked lists or who knows what else. You know? That's when some things cannot be done with a single stack. But a stack can simulate a counter. It's something more than a counter, a string. Because these don't have to be unary, they can be A's and B's. But you can only access the end of them, not the entire value of the stack, and that's restricted. Okay. So now, here's the first non-closure property. The context-free languages are not closed under intersection, unlike regular languages, which are closed under intersection. So now you know why we had this thing first. Closure under intersection with regular languages, we proved it. But they're not closed under intersection. How would you prove that? What kind of proof technique do you think will prove this?
I get the same parallel simulation, but then the stacks will have.
Okay, so she's saying if you try the cross-product construction on this, the simulation could mess up. What can go wrong in the simulation if you try to simulate 2 PDAs using 1 PDA? The stacks will clash. One PDA could be pushing onto the stack, the other one could try to pop off of the stack, so what are you going to do to simulate it? You can only do one or the other, you can't do both. Right? And still be consistent and still simulate both of them as if nothing happened. How many see that? So the stacks will clash. Why didn't it clash over here? Because one of them didn't need a stack, so there's nothing to clash. One of them used a stack, sure, so we'll let it use a stack of the simulator. This didn't need a stack for the FA, so that's okay. Now, both need stacks, so it clashes. How many say that's a proof? How many say it's not quite a proof, it's an intuition? Good. Now you're getting it. I'm proud of you, my Padawans. Why isn't that a proof? Well, so I say, so stacks will clash. Okay, is that a disproof? That they're not closed under intersection? Why isn't it a proof? Yeah.
It's showing that one proof method doesn't work.
Yeah, it shows that this straight raw simulation using parallel simulation with trying to simulate 2 stacks with a single stack, that doesn't work. Doesn't mean there's no cleverer way of doing it. Okay, just because one way didn't work doesn't mean no way worked. So you need to do something stronger than that. I understand why this is not a proof. Okay, but it's good intuition. How would you actually prove it? That you cannot do a parallel simulation like that with a cross product of 2 PDAs yielding a single PDA that recognizes the intersection. How would you prove that? Yeah. Counterexample. Obviously, the counterexample will show it. So how would you come up with a counterexample? Give me a counterexample of 2 context-free languages whose intersection is not context-free. And let me give you a hint. So this language here, 0 to the n, 1 to the n, 2 to the m, let's say if this was 2 to the n, that's not context-free, it turns out. So I'll give you right now as a free theorem, don't have to prove it. We can prove it using the pumping argument, but we'll get to that. 0 to the n, 1 to the n, 2 to the n is not context-free. There's no way to do it with a stack. Let me give you an intuition why. if you can compare the number of zeros to the number of ones by pushing and unpopping, you can do that, compare these two. Or you can flush all the zeros and compare these two. But you cannot compare all three together to each other. Because you can push the zeros, but then you have to flush them against the ones to compare to the ones. Or if you compare the ones, push the ones, you have to flush them against the twos to compare to the twos. But then you lose track of the zeros. That's the intuition, it's not a proof. But that's roughly the intuition why. But let's assume that this is not context-free. Okay? I'll give you another hint that 0 to the n, 1 to the n, 2 star, that is that context-free?
Yes.
0 to the n, 1 to the n, 2 star. Why is that context-free?
Because that's regular.
You don't have to count two.
You don't have to count the twos, right? All you need to do is compare the zeros to the ones, which is what we did already, and then flush the twos down the toilet. You don't need to count them. And you're still checking this condition, and you're good. So this is context-free. That's a hint.
0 star, 1 part n, 2 part n, you can take the other languages.
Yeah, so if you intersect this language, which we know is context-free, with another language, 0 star, 1 to the n, 2 to the n, what is the intersection of these two languages?
Context-sensitive.
It's this language here. So one of them is 0 to the n, 1 to the n, 2 star. One of them is 0 star, 1 to the n, 2 to the n. So you flush the zeros compared to the ones to the twos, and that's context-free again. So here's context-free, intersect context-free, giving you a not context-free language. And that's a counterexample, and that falsifies this would-be theorem that they're closed on the intersection, so they're not closed on the intersection, which is different than what finite automata are doing. Those are closed on the intersection. The regular language are closed. How do you understand this argument? So it's a counterexample. Any questions? And they're not closed under complementation either. So with the regular languages, all these were closure properties. Union, closure, intersection, complementation. The regular language will close under all of those things. Context-free, not so much. They're closed under the first two and the third also, but not the last two. Why is that true in 2 words?
De Morgan's.
The Morgan's law. How many see the Morgan's law here? Only 2 people. So think about it for 10 seconds. Why is this true by the Morgan's law? Now, this last thing.
The union is closed, but intersection is not, then the complementation of that should be not closed.
So what is the Morgan's law in terms of
In terms of the set of strings accepted by, say, 2 languages L1 and L2.
so L1
Union L2.
let's say L1 intersect L2 is equal to what?
L1 union L bar, L1 bar, union L2 bar, whole bar.
I could have put this bar over here, right?
Yeah.
How do you understand that? So sets, logic. So the Morgan's law, right? The complement of the intersection is the union of the complements. Another way of saying it, the complement of the and is the or of the complements in logic, right? The Morgan's law. So let's put the bar over here. Doesn't matter which side you put it over, you still get the identity. The intersection of 2 things is the union of their complements, all complemented one more time. How do you believe that? By that? Okay. So we already know we have closure under union. How do we know? Because we proved it right here. What was the proof?
Cross product.
Cross product or parallel
Palindrome.
simulation, same as a cross product, or
Non.
No, the grammar.
grammar.
Going non-deterministic.
Grammar proof. So we know the union preserves context-freeness. Now, if intersection was context-free, we know it isn't, but intersection is represented as this. And if complementation preserved context-freeness, then L1 complement will be context-free, because L1 and L2 are context-free, right? So L1 will be context-free if complementation preserved context-freeness. So will L2 bar be context-free. The union is context-free because that preserves context-freeness. And complementation yet again preserves context-freeness up here. So the whole right side will be context-free if complementation preserved context-freeness. How would you believe that? Okay. But the whole right-hand side is equal to the left-hand side, and equal things must have equal properties, aside from being equal in value. So the left-hand side would be context-free also. But that means that the arbitrary intersection of two context-free languages would be context-free, but it isn't. That's another theorem we have on this slide. Intersection doesn't preserve context-freeness, so complementation can't preserve it either. And that's a proof by De Morgan's law. How many understand this? Okay, any questions about that? So that was like probably the easiest proof on this slide because it followed immediately from the other proofs plus De Morgan's law. And this proves something even stronger, that context-freeness doesn't preserve, that context-freeness is not preserved under complementation. It proves something actually stronger. What is the meta-theorem? It's that this is just a corollary. I'll start it off and you tell me. This essentially also proves this argument that if you have some closure property in some class of languages, I don't care which it is, context-free languages, regular languages, decidable languages, recognizable languages, languages in NP, languages in P space, linear time recognizable languages, and there's infinite number of classes, right? Context-free is just one class. But if you have some class of languages that's closed under union and not closed under intersection, then what else can you tell me about this class necessarily? It's not closed under complementation either, automatically. You don't have to do anything beyond that. You don't have to go into counterexamples, you don't have to go into power set or cross-product constructions. It follows strictly from the other two properties because of De Morgan's law. Right? So these three properties, intersection, union, and complementation, they're related to each other by De Morgan's law. So if you have closure under both of these, complementation and union, automatically you have closure under intersection. How do you see that? If you have closure, but if you have closure under union, but non-closure under intersection, the third one must also fall and not be true, not be closed. So if as long as one of the three fails, one of the other two must fail too, and possibly both. So we just proved something even stronger than this thing about context-free language. We proved about any class of language whatsoever. We proved it about decidable languages, about recognizable languages, about languages in NP, like NP-complete languages, whatever. So that's a very strong result, actually. Okay, any questions about any of these? So we proved 5 different theorems in rapid succession, and many of them we proved 2 different ways. Questions? All right, let's take a short break. We'll come back. We'll talk more about this stuff, and it'll be fun.